Ladies and gentlemen, welcome to Hong Kong IE Civil Division event, technical webinar on shedding lights on seismic metamaterial design from the perspective of multidirectional wave attenuation, organized by the Hong Kong IE Civil Division and Polytechnic University. I'm the MC of today's webinar. We are honored to have Dr. Kai Chow, who is currently an assistant professor in Department of Civil and Environmental Engineering at the Hong Kong PolyU. He received his bachelor and PhD degrees from Chongqing University and University of Connecticut, UConn, respectively. After graduation, he worked in the Bentley Systems as a research engineer for civil engineering software development, and then returned to academia as a postdoctoral researcher at UConn, with the key focus on uncertainty quantification in advanced manufacturing process, funded by Air Force Research Lab in the USA. Without further ado, I would like to invite Dr. Zhou to deliver the talk. Dr. Zhou, please.
All right, yeah, thank you for the introduction by Vienna. Really happy to be here to present my work. And before talking about my own topic, I would like to share a little bit information about our department and highlights our achievement to promote a little bit of our department's image. That's my duty, as I say. So the key aspects of our success is the global recognition. We actually have made the significant stride on these areas. For example, in our department, we have like totally 28 staff members who are among the top 2% highly cited scientists all over the world. For the detailed information of the rankings, please refer to the right side figures. So you can see the details here. On the overall speaking, our department ranks the first in Hong Kong. More specifically, our department holds the third and the second positions in the civil engineering and transportation science and technologies, respectively. The ranking of the other areas are also pretty good, as you can see some ranking numbers here. Other than that, our department colleagues have also received both the international and national recognitions and titles through their great academic achievements. Currently, our department has one member of the Chinese Academies of the Science, 7 Changjiang scholars, 1 fellow of the Australian Academies of Engineering and Technology, and 1 fellow of the Royal Academies of Engineering UK. So in terms of the funding acquisitions, we have these remarkable progresses over the past several years. For example, we have obtained the 4 largest RGC funds, known as the scene-based funds, in the last 4 years, thanks to the efforts by the Professor Ni, Professor Li, Professor Tan, and Professor Wang. Each project amounts to approximately 40 million Hong Kong dollars or even higher. Besides this, our department also has secured the other substantial grants, each amounting approximately $5 million, such as the Green Tech Fund, which is secured by our department head, Professor Peng, and Professor Li. Professor Peng also has been awarded as a Liaotong Conservation Fund, which totals around $2 million, which are a great achievement. As we all know, the RGCs also offers some other significant funding opportunities, such as the Collaborative Research Fund, CRF, and the Research Impact Fund, RIF. Our department has demonstrated the research excellence through securing a number of this type of the funds. So the detailed information can be seen in this page. In the time of interest, I would like to skip the details so you can very generally see some big pictures here. In terms of the educational development, our department currently has offered 3 different programs in terms of the different levels. We have the undergraduate programs, a postgraduate program, and the research postgraduate program. So for the undergraduate programs, we have the 1 schemes, bachelor schemes in civil engineering and sustainable development. For the postgraduate programs, we offer like 2 sub-programs. Named the Master of Science in Civil Engineering, the Master of Science of Environmental Management and Engineering. And for the research postgraduate programs, we offer the Master of Philosophers and the PhD degree programs. So we do encourage the talented and interested students to apply for the programs and to be the part of the CE family. So over the past several decades, our department has nurtured numerous exceptional professionals. Presented here are some distinguished alumni who have already received the notable reputations in their respective industries. I think most of them are working in Hong Kong, so you probably know some of them. We would like to express our gratitude to their continuous effort and contributions to our department over the years. So talking about the facilities, our department currently has 30 laboratories, 2 workshops, and 1 research centers in Shenzhen. Those resources actually can provide a solid foundation for the academic staff to pursue the success of the research. So for the details of those facilities, I suggest you guys can, go to our department homepage. You can find all the information about those laboratories, workshops, and the research centers. To conclude, in the last page, I just want to provide some social media plan for. If you are interested, you are welcome to scan those codes and join our community. We are committed to further enhancing our department's image and reputation through the ongoing research and educational achievements. So thank you very much for attention for this specific document about our department's information. Then I will switch to another topic, talking about my research. All right, good afternoon, everyone. I want to say it again. I'm very glad to be here. It's an honor for me to present the research topic, which our group has been conducting since I joined the PolyU last year. So the title of this presentation is Shedding New Lights on Seismic Metamaterial Design from Perspective of the Multidirectional Wave Attenuation. This talk, like the other talks, are very similar, covers 4 main sections: background, introduction, research objective, and overview, theories and approaches underlying this research, case implementations, and the final remarks and the future outlooks. The theme comes the first would be the background of this research. So this research topic is about the earthquake mitigation. So it is very essential to examine the historical and the demographic data on the earthquake occurrence worldwide. So according to the map shown here, there's a significant number of the earthquake occurred between the 1900s and 2017, primarily concentrated in the several seismic zones. Although the earthquakes may not seem tangible in Hong Kong, it's worth noting that a major earthquake struck Shantou in 1980, which is relatively close to our locations. So due to the unpredictable nature of the earthquake, mitigation of the earthquake actually will become very important. So beyond the 2020s, there have been several major earthquakes with magnitudes around 6 or even higher. And the recent seismic events have had fatal consequences on the infrastructures and resulted as a significant loss of the lives. So you can see those figures in the page. So this slide just gives us several examples of the earthquakes and their destructions, in different cities all over the world. So starting from this page, I intend to introduce the earthquake and the current earthquake mitigation measures from a more technical perspective. So the negative impacts of the earthquake are quite apparent, which have been mentioned in previous section. So if looking at earthquake more deeply from the wave perspective, the earthquakes comes with a seismic wave due to the rock ruptures in the earth. As can be seen, the right side schematic here. So I change the pointer. This is a schematic to show the earthquake actually always comes with a seismic wave. So the two types of the waves that are included here, named the buckle wave and the surface wave. The buckle wave propagate within the media, while the surface waves, as the name indicates, propagate at the surface of the media. So compared to the buckle wave, the surface waves are more particularly destructive. So the energy carried by the seismic wave is dominated by the low frequency components. There's various traditional seismic metamaterial methods and approaches have been developed and adopted, including but not limited to different types of the dampers and the isolation bearings. However, the shortcoming remains for those devices due to the issues related to the inconvenient device deployment and undesigned mitigation performance. That actually becomes the major incentive of our research, which proposed to use so-called the seismic metamaterial concept to seek the performance enhancement of the seismic mitigation. So like the general metamaterial, the seismic metamaterial has unit cells with specific arrangement patterns. So there is a fundamental properties associated with the single or individual unit cell, so-called band gap. So the band gap defines the frequency range within which the wave theoretically can be completely blocked. So the band gap in this context is an indicator, to guide the unit cell design. So the wave blocking inherently is achieved by the energy trapping mechanism. For the seismic metamaterial, the local resonance is a very popularly used mechanism, which shows the significant relative motions between the parts in the unit cell. With the local resonance, the surface wave can be attenuated at the surface areas, and at the same time, some of it can be converted into the buckle wave, as illustrated in the animations shown here. So this surface wave propagates through the surface, and when it goes down, it becomes the buckle wave. So thus elevating the destructive effects of the surface wave. So according to the comprehensive literature review, the general seismic metamaterial include the non-embedded, partially embedded, and fully embedded seismic metamaterials, which offers the context for our subsequent seismic metamaterial design. Fundamentally, seismic metamaterials are intended to interact with the seismic waves, which has the extremely long wavelengths. So as specific type of mechanical metamaterials, the general structure of the seismic metamaterial can be adopted to adjust the various type of the waves, making them applicable across the engineering fields. For instance, they have the potential, to enhance the general vibration control and reduce the structural noise resulting from the vibration. So therefore, the construction, the transportation industries which experience the significant noise levels can greatly benefit from this research. So the right top figure here just give us previous studies which leverage the metamaterial development to mitigate the railway noise. Although the seismic metamaterials are an emerging technology, the research on their development and the design is still in its initial stage. So as you can see, most of the published studies have been conducted very recently, from the 2019 to 2024. So this also reflects a rapid growing interest in these areas of research. So through the extensive literature review, it is found that most studies have focused on brainstorming the structure of the seismic metamaterials and validating their performance against the predetermined incident seismic wave. However, it should be very important to note that the direction of the incident seismic wave is generally unknown due to the unpredictable essence of the earthquake. So developed seismic metamaterial thus cannot always guarantee the consistently excellent performance for incident waves with any possible directions. So which highlights a gap that need to be addressed for the practical implementation. So the question raised here is pretty natural. Can our research provide any potential solution for this issue? Considering the challenges discussed above, let's introduce the research objective and overviews of these studies. So let's take a first glance of this research in advance. So as shown in this framework or in this picture, our goal basically is to design the effective seismic metamaterial that can enhance the multidirectional wave attenuation considering the actual scenarios. So to achieve this, we'll employ a hierarchical design framework that will optimize the unit cell structure and the patterns in a sequential manner. So throughout the different design stages, we'll formulate a specific metric shown here, to guide the whole design process. So later on, I'll explain the more details about our research efforts to accomplish this seismic metamaterial design. Before stepping into the official content for the design showcase, it's very necessary to introduce the theories and approaches behind these studies that support the seismic performance evaluation and design. So now, let's just jump into the new sections to cover those contents. As mentioned, the band gap is a very important property of the unit cells. The band gap can only accurately reflect the behavior of the entire seismic metamaterial when assuming that there are an infinite number of the identical unit cells are arranged in the metamaterial. Mathematically, such an assumptions can be achieved, by applying the ideally periodic boundary conditions on the sides of the one typical unit cells using the flow theories. So in this context, the band gap is an ideal metric for seismic metamaterial performance assessment. With the boundary condition imposed, the Garmini equation. The Garmini equation for the band gap analysis can be formulated as shown here, these two equations. So the top equation here is the displacement relation enabled by the periodic conditions, where the A is a very important parameter. So I wanted to give some background. The A here is a lattice constant to define the distance between two adjacent unit cells, considering a seismic metamaterial consisting of multiple unit cells. So the equations underneath here is the dynamic equations based on the finite element series in the pure mechanical or structural domain, and the incorporations of the above mentioned periodic boundary conditions. So as can be seen in these equations, I think you should be very familiar with this one, because I believe a lot of audiences are structure engineers. So the band gap analysis shown in these equations essentially is a model analysis in terms of the wave vectors within the metamaterial plane. So at different wave vectors, we actually can compute their natural frequencies and mark them in the plot as illustrated in the right side figure here. So the curve generated through those data points are known as the dispersion curves. So the slope of the data points on the curve represents the wave velocity, which is inconstant in dispersive medias. So the gap between those curves is defined as the band gap, highlighted with these gray colors. Notably, the topmost curves is known as the sound line, is distinctive features of the seismic metamaterials. It represents the envelope for the surface wave domain, which is the features absent from the dispersion curve of the other metamaterial types. Furthermore, since the band gap analysis is performed upon the unit cell model, and the size of the unit cell models is significantly less than the size of the entire seismic metamaterial model, the computational cost of the band gap analysis is quite cheap. Recall that the band gap is an ideal metric which can be used, for the initial unit cell design. Besides, in a realistic setting, the band gap is not measurable. Instead, it can be only estimated via the frequency domain analysis. So when treating the seismic wave propagation as a dynamic problem, the output or response of the wave of the host structures, all right, in the frequency domain, given the wave input, can be described, in this dynamic equations. That's very basic equations. So the frequency domain analysis can yield so-called transmissions, which can be used as a generic indicators to evaluate the performance of the actual seismic metamaterials. In other words, the transmissions is a more realistic system-level measures to quantify the performance of the seismic metamaterials. So the transmission, you can see this equation is mathematically defined as a log functions, where the U2 here and the U1 here represent the displacement of the output areas with and without the seismic metamaterials, respectively. Obviously, according to that equation, the smaller the transmission value is, the better the wave attenuation effect. It is worth noting the current investigation primarily rely on the one-dimensional frequency domain analysis, short for the 1D-FDA for the transmission calculation. So from a numerical modeling perspective, the ideal periodic conditions are applied to the surface of the seismic metamaterial here, perpendicular to the directions of the wave propagations in this 1D FDA. So the perfectly matched layers are set at surrounding soil layers to absorb the unwanted waves in this FDA. So these conditions are illustrated in these figures. Therefore, the 1D FDA only allows us to assess the transmissions in the case of the unidirectional wave propagation, which we assume the wave propagates in this direction from the left to right. You cannot do it from the outward to the inwards. So that's the limitation. All right. So in addition to this limitation, imposing the periodic conditions results in an idealized seismic metamaterials, assuming an infinite number of the unit cells arranged perpendicular to the wave propagation direction. So this assumptions actually, again, is very ideal. It does not align with the condition for the actual deployment of the seismic metamaterial. So on the other hand, the simplified approach, which here is 1D FDA, can enhance the analysis efficiency because the periodic condition essentially, show these two equation comparisons. This periodic conditions essentially can reduce the size of the entire seismic metamaterials for analysis. Despite the good computational efficiency, this conventional approach is not able to support our research, which aims to conduct the seismic metamaterial design based on the multi-directional wave attenuation performance. So how to do it? How to address the limitation of the current available approach? So to assess the multi-directional wave attenuation performance, so we have to jump out of the box and develop a new frequency domain analysis approach. So intuitively, we can remove, the periodic conditions applied on the seismic metamaterial models, which allows one to solve the above-mentioned two issues concurrently. So this new approach is referred to as a 2D FDA, two-dimensional frequency domain analysis. So schematics of this model in the 2D FDAs is illustrated in the right side figures. So in this slide, we just want to compare, the 2D FDA and the 1D FDA to clearly demonstrate the shortcomings of the 1D FDAs due to the ideal assumption setup. Specifically, we implement the 2D FDA by varying the number of the unit cells perpendicular to the wave propagation directions and compare their transmissions with that from the 1D FDAs. As you can be seen from the left bottom corner figures here, the discrepancies between the 1D FDA and the 2D FDA results reduces when the number of the unit cell increases. So this indicates that the 1D FDA can only approximate the performance of the actual seismic metamaterials with relatively very small errors only when the number of the unit cells reach certain threshold, illustrating its limitations in actual practice. So in contrast, the 2D FDA actually is more generic, capable of modeling any possible seismic metamaterial configurations and evaluating the respective performance. So in 2D FDA, however, the trade-off always remains, along with the growing computational costs in the 2D FDA. Obviously, increasing the number of the unit cell will increase the model size, leading to a higher computational cost. Because of the periodic conditions, the 1D FDA holds a significant advantage over the 2D FDAs in terms of the computational efficiency, as can be observed, in the right bottom corner figure here. So they'll give you some details about model size and also the time required for completing the analysis. So to enhance the computational design of the seismic metamaterial, improving the efficiency of the 2D FDA is very critical. So this slide just introduces a general strategies for computational the acceleration. So the concept here is pretty straightforward, I would say, which is to leverage the symmetry, the inherent in the seismic metamaterial structures. So that when a target seismic metamaterial exhibits the geometric symmetry, we could assume, that wave field information remains the same at the location symmetric to the central plane, to the central plane, as shown in the right side figures here. Mathematically, this operations resembles the coordinate condensations in the general order reduction approach in structure dynamics. So consider the seismic metamaterial structure shown here, in these figures. We further perform both the full-scale 2D FDA and the symmetry-based 2D FDA, comparing their transmissions given in the middle figures at the bottom of the slides. It's evident that the high accuracies can be achieved by using the symmetry-based 2D FDA. Additionally, we investigate the computational time of these two types of FDAs, as shown in the left side corner figures here at the bottom of the slide. So the nearly halved model size leads to substantial reductions in computational cost, demonstrating the feasibilities of this computational strategy. It should be noted that the certain actual or plane symmetries often used as a physical constraints is frequently required in the actual seismic metamaterial design. Therefore, these computational strategies can be broadly applied to enhance the computational efficiency and thus facilitate the hierarchical design proposed in this study. So based on the theories and approaches reviewed, we can adopt them to conduct so-called case studies and discuss the relevant results. We will first develop the unit cell aiming at finding its optimal topologies based on the bandgap information. So here we'll try to explore the different type of the unit cells mentioned earlier. Above the soil, fully embedded, partially embedded. I just want to record those informations for your reference. So we began by designing a unit cell consisting of a square steel and the surrounding soil. The topology here is relatively simple. The detailed configurations can be seen in the figure shown here. So A here again is a very important parameter I mentioned earlier. A is a lattice constant, which has been introduced. All right, so it is used to determine how much surrounding materials are involved in a unit cells. So which is an important performance related parameters. So in this research, this parameter is selected upon the literature review instead of the rigorous design optimization. So we start to put these columns totally above the ground, so-called the non-embedded unit cell. So in this unit cell, the surrounding materials becomes the air rather than the soil. So I just want to clarify this. All right. So by carrying out the bandgap analysis, we can find the bandgap shown here. So the bandgap here is very narrow, about 2.6 Hertz bandwidth for this unit cell shown in these figures. So one particular mode shape of the unit cells at point A1 in the dispersion curve is extracted to demonstrate the local resonance effect for the wave absorption. Then we embedded the same columns into the soil, just a part of the same column, not just the whole columns, just a part of the columns into the soils to form so-called the partially embedded unit cell. And we observe, the bandgap here, it becomes wider. It's about 6 Hertz bandwidth, showing the better performance. So some mode shapes, is at point, B1 and B2 on the dispersion curve are retrieved, for showing, how the unit cell is able to formulate the bandgap utilizing the local resonance. So based on these results, we are thinking about if there's any further possible enhancement. So for following a very similar idea, how about we embed the entire columns into the soil and check what will happen, what will be going on. So setting aside the bandgap based performance, so the embedded unit cells offers distinct advantages over the other unit cell types, non-embedded and partially embedded. Firstly, it avoids the view obstructions, providing an aesthetic benefit. Secondly, it exhibits high durability during the extreme weather conditions compared to the non-embedded unit cell. Most importantly, it does not occupy the land space above the ground, making it particularly suitable for the urban setting. However, when we examine its bandgap, and intriguing observations emerge. You can see the bandgap dispersion curve here. The bandgap is completely disappeared. So this actually represents a worst case scenario. The fundamental reason is that the local resonance is disabled because the soil completely restricts the motion of the columns according to this design when the unit cell is fully underground. So the mode shape at the left part of the dispersion curve are denoted by C1, C2, and C3. Also demonstrate quite small motions of the steel columns. So considering that the bandgap is an ideal metric, so that's some key information I want to record again. So we want to further conduct the so-called the FDA of the seismic metamaterials with involving this type of unit cells. It is surprising that we still can see some wave attenuations from these transmissions, All right. So the wave attenuation can be over certain frequency range, even the frequency range is not very wide. So such mismatch is due to the many factors, to the best of our understanding. This may be caused by the wave reflection within the seismic metamaterials that might exist. Moreover, the band gap analysis is adopted to quantify the wave blocking performances under the sound line. In other words, it is specifically intended to cope with the surface wave instead of the buckle waves, while the parts of the buckle wave may still occur in FDA. So the above results allow us to rethink the unit cell design. So given the non-performance related advantages of the embedded unit cells, we still prefer to adopt this type of the unit cells for our seismic metamaterial design. So, but the question is how to reactivate and even further amplify the local resonance effect when the unit cell is fully on the ground. So in this research, we developed a new configuration of the unit cells as given in this figure. So compared to the original unit cell presented in last slide, this new unit cells has more complexities in topologies and structures. So basically, this unit cells consists of the one outer columns and the one inner columns. Between them, there is a rubber plate, so aimed at providing the soft coupling. So this essentially can yield the impedance mismatch, which is able to amplify the local resonance of the unit cell. So according to this good design, even restricted by the surrounding soils, the design can amplify the motion of the columns, especially the inner columns. So the band gap upturn through this analysis is extremely wide. You can see the dispersion curve and the band gap here around the 13 Hertz bandwidth, almost covering the whole areas under the sound lines of the dispersion curve. The results matched our expectations of the designs, which clearly, verify our design philosophy. So to emphasize, the visibility and the strength, of our unit cell design, so we involved some benchmark studies conducted upon the theme design objective, which aims to maximize the band gap width. So specifically, we compare our results with those from other 5 studies, and the band gap outcomes are summarized, in this table. Each study exhibits the distinct individual band gaps. So using the total band gap width as a performance metrics, it's clear, that the unit cell developed in our studies achieved a wider band gap, which reconfirms the success of this unit cell design. Having designed a well-structured unit cell, we proceed with the seismic metamaterial synthesis. Our seismic metamaterial consists of an 8x8 array of identical unit cells, as described in the figure shown here. Due to the uniform distribution of the unit cells, we refer to this configuration as a periodic seismic metamaterial. It serves as a baseline for subsequent design comparisons and performance validation. So the numerical setup for the entire seismic metamaterial model is provided in the top right figures. So we then can conduct a 2D FDA, on this metamaterial models to obtain its transmission. So because this is a periodic seismic metamaterial with all identical unit cells, and the number of the unit cells perpendicular to the wave propagation directions in this seismic metamaterials appears sufficient. So we put the transmissions and the band gap from the earlier band gap analysis together here, and finally, they are in good agreement, validating the modeling approaches and the procedures are used in both the band gap analysis and the 2D FDA. So however, the slight mismatch, as you can see here, at the areas of the first band gap. This This discrepancies likely stems from the operational assumptions made during the bandgap analysis, which does not fully align with the conditions in the actual deployment of the seismic metamaterials. Building upon the hierarchical design concept, as I mentioned, in the very beginnings, it's natural to propose ideas regarding the unit cell pattern explorations to further enhance the wave attenuation performance. So starting from this slide, I will proceed with the pattern design using the periodic seismic metamaterial as a baseline or benchmark. As we know, the design space for the unit cell patterns is very vast, allowing for a wide range of the aperiodic configurations. So the question arises, can we find an aperiodic patterns that enhances the performance? Intuitively, the answer should be yes, because the increased dimension of the design space opens up the more possibilities. However, searching for an optimal aperiodic patterns within such a large space is computationally demanding. So balancing the design cost and the feasibilities hence becomes very necessary. So in these studies, we explore the graded patterns of the unit cells. The graded patterns introduce a specific geometric constraints during the pattern generations, mitigating the optimization costs. So previous research shown here, has already demonstrated that the seismic metamaterial with one-dimensional graded patterns could achieve success in unidirectional wave attenuations under predetermined incident wave. So inspired by these findings, we considered the possibility of enhancing the multi-directional wave attenuations by developing two-dimensional graded patterns for the seismic metamaterials. So to verify these ideas, we will analyze and assess the seismic metamaterial with the different potential pattern arrangements. And it should be noted here that the non-graded seismic metamaterials, non-graded patterns, non-graded seismic metamaterial is the same as the periodic seismic metamaterials I mentioned above. In this research, so we defined the three mathematical functions, the one linear functions and the two polynomial functions to guide the generation of the graded patterns for our seismic metamaterial. Specifically, we create a seismic metamaterial with a three one-dimensional pattern and the three two-dimensional patterns for subsequent analysis. To accurately describe the seismic metamaterial configurations, we establish a coordinate system that indicates both the pattern gradient and the wave propagation directions. So in this study, we consider evaluating the multidirectional wave effects under like 4 wave propagation directions. So the 4 one-dimensional graded seismic metamaterial x-axis represents the pattern graded directions. So all one-dimensional graded seismic metamaterial except the symmetry about x-axis, hence their performance when the wave propagates along the negative and positive y-axis should be identical, such there are 3 cases to be analyzed. Similarly, for the two-dimensional graded seismic metamaterial, the pattern gradient can be along both the x and the y-axis. Their performance when the wave propagates along the negative x and the y-axis should also be the same, as should their performance when the wave propagates along the positive x and y-axis. So there are totally 2 cases to be analyzed. So besides, we will improve the two-dimensional frequency domain analysis to calculate the transmissions for multidirectional wave attenuation performance assessment. So we began by comparing the results of the non-graded and the one-dimensional graded seismic metamaterials. So the detailed results are presented here as mentioned due to the configuration symmetries of the one-dimensional graded seismic metamaterials. We performed the numerical analysis for the 3 distinct wave propagation directions for each of the representations named x plus, x minus, and y Y plus or Y minus wave. So for each case, we compare the transmissions of all four seismic metamaterials. Overall, the 1D graded seismic metamaterial exhibited better performance across the most of the frequency range of interest than the non-graded seismic metamaterial. The improved performance of the 1D graded seismic metamaterial is particularly noticeable from the 4 to 14 Hz under the X plus wave, and from the 4 to 13 Hz under the Y plus or Y minus wave. In contrast, the non-graded seismic metamaterials only demonstrates the desired attenuation performance over a relatively narrow frequency range, about like 2 Hz, 2 Hz wide. However, upon the closer examination of these figures, the middle figures, it becomes very difficult to conclusively claim the advantages of the 1D graded seismic metamaterials compared to the non-graded seismic metamaterials in terms of the wave attenuation performance under the X minus wave. So additional quantitative analysis and comparisons are required. To facilitate the comparison and assessment, we then define an index, so-called the average transmissions, with the mathematical formulations given here. So these quantities can account for the contributions of the both frequency attenuation band and amplitude reduction, providing more comprehensive measures for the performance assessment. So we calculate the average transmission of the all four one-dimensional seismic metamaterials under the three-wave propagation cases, and collect the respective index values as included in this table. So because of the four geometric symmetry, so the non-graded seismic metamaterial shows the same attenuation effect regardless of the wave propagation direction. So when we look at the last column of the tables, we can see the one-dimensional graded seismic metamaterial significantly outperform the non-graded seismic metamaterial in terms of the multi-directional wave attenuation performance. So other columns in the tables gives the results corresponding to the different wave propagation cases. So clearly, the 1D graded seismic metamaterials work more effectively when the wave is assumed to transmit along the positive x-axis. This improvement also is captured for the case that the wave transmits along the y-axis. Interestingly, there's no significant difference, among the results for the wave propagation along the negative x-axis for the all compared seismic metamaterial. So this observations aligns with the findings from the last slide, emphasizing the importance of considering the pattern gradient orientations when deploying the seismic metamaterials in practical implementations. So it also highlights the limitations of using the unidirectional wave attenuation performance as the only criteria for the seismic metamaterial design. So taking a different perspective, we visualize the results by comparing the performance of the same seismic metamaterials on the different wave propagation cases. As expected, the findings remain consistent. So the new result display highlights the correlation between the orientation of the pattern gradient and the wave propagation directions indeed impacts the performance. So such insights obtained from this analysis is very valuable. So we further conduct a detailed analysis of the performance of the 2D graded seismic metamaterial. For the time of interest, I want to go through the detail very quickly because I just checked my phone. It's 5:50. So for the 2D graded seismic metamaterial, please keep in mind that the two distinct wave propagation cases will be analyzed using the two corresponding figures shown here. So for each wave propagation case, the transmission of the three 2D graded seismic metamaterials are put together for comparison. So when the X plus or Y plus wave is considered, the seismic metamaterials with 2D polynomial pattern 1 actually has the best attenuation performance over the 5 to 8 Hertz, while the seismic metamaterial with the 2D polynomial pattern 2 has the best attenuation effect at the frequency exceeding the 10.5 Hertz. Additionally, it seems that the graded seismic metamaterial with the 2D linear and polynomial patterns show the very similar performance, especially over the 8.5 to 16 Hertz. All right, so we also can get some other observations from the results. Once again, I just want to skip those details. So while no two-dimensional graded seismic metamaterial completely dominates the others in terms of the performance for the specific wave propagation directions. All right, so here we just like what we did before. We wanted to view the results for the same seismic metamaterials under the different wave propagations. So the conclusions actually is very similar. This seismic metamaterial exhibits the superior performance in the high frequency range between 8 to 16 and the 16 Hertz under the X plus wave or Y plus wave, compared to the X minus and the Y minus wave or Y minus wave. All 2D graded seismic metamaterial have the very similar performance under the X plus or Y plus waves. Besides, the seismic metamaterial with the 2D polynomial pattern 1 actually achieved the best overall performance, or the multi-directional wave attenuation performance, with the average transmission around minus 14.31 dBs. That's a big value. And now we put together the average transmission index values for both the one-dimensional and two-dimensional graded seismic metamaterial. So these results are displayed using the bar plots that highlights the comparative performance between these 2D graded seismic metamaterials and their 1D counterparts across the different wave propagation cases. So for clarities in visualizations, we use the absolute values of the average transmission, and ensuring all values are positive to facilitate the comparison. So the data here clearly show a significant enhancement in all performance metrics for the seismic metamaterial with the 2D linears and the polynomial pattern 1 over their 1D counterparts. So specifically, the seismic metamaterials with 2D polynomial pattern 1 demonstrates the most substantial overall performance gain with reductions of the 2.29 dBs. In contrast, the seismic metamaterials with the 2D linear patterns and the polynomial pattern 2 only can enable a slight improvement with a modest reductions around 0.71 dBs when compared to their 1D counterparts. Finally, we aggregate the overall performance of the all studied seismic metamaterials and present the results using a radar plot here. So that would be much clearer. Obviously, the 2D graded patterns indeed are very effective for multi-directional wave attenuation. So among the 2D graded seismic metamaterial, the graded seismic metamaterials with the 2D polynomial pattern 1 exhibits the best overall performance. So those results altogether clearly validate the effectiveness of the design ideas and the frameworks developed in this research. So here comes the final remarks and the future plan. So this research includes several key contributions and outcomes. A hierarchical framework consisting of the unit cell configurations and the pattern designs is developed. A new design metric refers to as the multidirectional seismic attenuations is proposed to guide the whole design process, which serves to inform the cost-effective seismic metamaterial deployment decisions. So to evaluate these metrics, a new modeling approach with integrated computational strategies is developed. So the seismic metamaterial involving the normal embedded unit cells with the 2D graded patterns presented in the comprehensive case studies demonstrate the visibilities of the design framework and the modeling approaches in this study. This is actually a newly completed work which are presented in this year's the SPIE Smart Structures Non-Destructive Evaluation Conference held in Long Beach, LA, this March. I'm glad that the results of this work has raised the interest of the many audiences. We did have a very pleasant discussions in relation to this topic, followed by some idea exchange for the further advancement. So here, just give the idea for the future research or future advancement. Looking ahead, our short-term objectives include further enhancing the efficiency of the modeling approach and pursuing the development of an improved seismic metamaterials capable of omnidirectional wave attenuations or the full-angle wave attenuations. Aware of the manual natures of the current design process, so our long-term goal encompasses the integration of the data-driven intelligence, the algorithms to facilitate the autonomous and efficient seismic metamaterial design. Additionally, we plan to explore the practical considerations such as the uncertainties inherent in the seismic metamaterial manufacturing and fabrications to ensure the robustness of the design solutions. In the end, I would like to acknowledge the significant effort put forth by my PhD student who conducted the whole analysis for this research under my supervision. Thank you for your time and attention as well. I'm more than happy to answer any questions you might have. Thank you.